even a baseball wasn't just a solid, predictable object, but also fundamentally a wave. What if the universe isn't as concrete and predictable as it seems? It's kind of a mind-bending question, right? Well, today we're diving deep into exactly that. We've got a fascinating stack of research in front of us, including some really incredible excerpts from the quantum symphony, from atoms to macroscopic reality. And it tackles this very idea of the universe's dual nature. So our mission for this deep dive is to unpack the incredible story of wave-particle duality, how it applies to all matter, and then most importantly, we're going to tackle an intuitive, but, well, ultimately flawed question. Does the wavelength of a baseball actually come from summing up the wavelengths of all its tiny constituent atoms?
Yeah, and this isn't just a dive into physics, really. It's more like a journey to understand how, though seemingly distinct quantum and classical worlds are, profoundly connected, and why our everyday experience of a solid, predictable reality is actually an emergent phenomenon. You're definitely in for some aha moments today, I think.
Okay, let's set the stage first. For centuries, classical physics had a very clear picture, right? Particles were like tiny billiard balls, and waves were, well, ripples on a pond, distinct things. But then, early in the 20th century, that foundation started to crack.
Exactly. You had the work of Max Planck and then Albert Einstein on the photoelectric effect. They basically shattered that traditional view of light. They showed that light, which everyone thought of as the classic waves, also acted like particles, discrete packets of energy called photons. This startling revelation of wave-particle duality for light really set the stage for something even bigger.
So light has this dual nature. Okay. But what about everything else, matter? That's the question Louis de Broglie tackled in 1924 with a really audacious proposal. He thought, if waves can be particles,
then why can't particles be waves? That was the leap. He suggested that all matter, not just light, has this dual nature, that there's a wave intrinsically associated with every single particle. It was a huge conceptual jump. It implied our familiar world of solid objects was, at a fundamental level, governed by waves.
And he even gave us an equation for it, didn't he?
He did. A simple but incredibly powerful equation. Lambda equals h divided by p. So h equals hp. Here, lambda is the de Broglie wavelength. H is Planck's constant, this fundamental, incredibly tiny number that kind of sets the scale for quantum effects. And p is the momentum of the particle, mass times velocity. Now, this equation shows a crucial inverse relationship. The greater particle's momentum, the shorter its wavelength. This is really key. It's why quantum effects are so obvious for tiny particles, but basically negligible for, a baseball.
Right. And the power of this idea was clear pretty quickly, wasn't it? Even before they had solid experimental proof. You mentioned it explained Niels Bohr's model of the atom. Bohr's model had these rules that seemed a bit arbitrary.
Yeah, they felt a bit ad hoc. Bohr's 1913 model worked. It explained the discrete energy levels in atoms, but his quantization rules were just sort of stated. De Broglie saw this really elegant analogy. Think of standing waves, like on a guitar string. He proposed that an electron's allowed orbit in an atom was simply one where its matter wave formed a stable standing wave around the nucleus, fitting perfectly. And that condition is only met if the orbit's circumference is an exact integer multiple of the electron's de Broglie wavelength. When he plugged his own equation into this idea, bam, he derived Bohr's angular momentum quantization condition. It provided a physical reason for Bohr's rule. It just suddenly clicked into place.
Okay, that's pretty neat. But theory is one thing. How did they actually prove that matter, like electrons, could behave like waves?
Right, the proof. That came from the Davisson-Germer experiment in 1927. Clinton Davisson and Lester Germer, they fired a beam of electrons at a nickel crystal. Now, if electrons were just tiny particles, you'd expect them to scatter randomly, like little bullets bouncing off. But that's not what they saw. Instead, the electrons produced a distinct diffraction pattern. Those patterns of bright, dark spots you get when waves bend around things.
Like light through a grating.
Exactly like that. Diffraction is the unmistakable signature of waves. And the pattern they observed matched precisely what de Broglie's formula predicted for electrons behaving as waves with that specific wavelength. That experiment, along with some others, really solidified wave-particle duality for matter. It means the physical world isn't made of waves or particles. It's made of quantum stuff that shows one face or the other depending on how you look at it.
So this applies universally to atoms, molecules, everything. It really challenges our everyday intuition, doesn't it? Which brings us perfectly back to that intriguing question you posed at the start. If everything has a wave nature, why can't we just add up those atomic wavelengths for a baseball? Seems logical, maybe.
It seems logical, but it misunderstands how waves actually combine. This is where the principle of superposition comes in. When waves overlap, the result is the algebraic sum of their individual displacements at each point. Think of water waves crossing the Argent. They add up where they meet, then pass through each other unchanged. For quantum matter waves, the displacement is the wave function's amplitude. And where that amplitude is high, that's where you're likely to find the particle. So the key is use sum amplitudes, not wavelengths. That immediately rules out just adding wavelengths together.
Okay, summing amplitudes, not wavelengths. What does that actually do when waves combine? What does it look like?
Well, that leads directly to interference. Constructive and destructive interference. Constructive interference happens when waves are in phase. So crests line up with crests, troughs with troughs. Their amplitudes add, making a bigger wave. Double the amplitude actually quadruples the intensity. Destructive interference is the opposite. When they're out of phase, a crest meets a trough, they cancel each other out. Amplitudes subtract, leading to a smaller wave, or even zero amplitude if they're perfectly out of phase and have the same initial size.
So the phase relationship, how they line up, is absolutely critical.
Absolutely paramount. And here's another key point. If two waves with the same wavelengths combine, the resulting wave also has that same wavelength. Only its amplitude changes due to interference. This again shows why you can't just add wavelengths. Furthermore, to even see clear interference patterns, the waves need to be coherent. That means they need the same frequency and a constant phase difference over time, like a laser beam versus the jumbled light from an old light bulb. And that coherence is a huge problem for macroscopic objects.
Yeah.
Think about the trillions of atoms in a baseball. They're constantly vibrating due to heat, right? All that thermal jiggling means their matter waves have random, constantly changing phase relationships. They're completely incoherent.
Like a massive crowd shouting randomly versus a choir singing in unison.
Exactly. There's no way to get a coherent combined wave from that random jiggling.
That makes sense. So this idea of a particle being just one simple sine wave is, well, too simple, because a single perfect sine wave would stretch out infinitely. The particle could be anywhere. So how do we describe a particle that's actually located somewhere, like an atom stuck inside our baseball?
Right, we don't use a single sine wave. We use what's called a wave packet. You build a wave packet by adding up or superposing many different sine waves, each with slightly different wavelengths and therefore slightly different momenta. These waves interfere constructively in one small region, that's your packet, where the particle is likely to be found. And they interfere destructively everywhere else, canceling out. So the wave function basically drops to zero outside that small region, localizing the particle. And remember, the square of the wave function's amplitude gives you the probability of finding the particle there.
Okay, a wave packet built from many waves. And this process, building this localized packet, this leads directly to Heisenberg's uncertainty principle, doesn't it?
It does, directly. It's not some weird extra rule. It falls right out of the maths of waves. To make a wave packet narrower in space, meaning, the position more precisely, small delta xx, you mathematically have to combine a wider range of different wavelengths. A wider range of wavelengths means a wider range of momenta, because wavelength and momentum are linked by de Broglie. So you have a larger uncertainty in momentum, a big delta p.
And vice versa, if you want precise momentum.
If you want precise momentum, you use fewer wavelengths, maybe closer to a single sine wave. But that makes the wave packet spread out more in space. Large. It's an inherent trade-off. X times that has to be greater than or equal to a small constant, h bar over 2. You can't know both precisely at the same time. And crucially, this isn't just about our measurement tools being clumsy. It's fundamental. It's baked into the wave nature of reality.
Wow. Okay, so let's connect that back to the baseball. The atoms inside the baseball are pretty localized, right? We know roughly where they are. Small x.
Exactly. They're confined within the structure of the baseball. So small x. Which means, by the uncertainty principle, each of those atoms must have a very large uncertainty in its momentum, a large up. Therefore, each atom isn't represented by a single wave with one specific de Broglie wavelength. It has to be a complex mix, a superposition of many different wavelengths. This completely demolishes that initial idea of summing up the wavelength of each atom. They don't have a single, well-defined wavelength to sum.
Okay, that really clarifies why the simple summation idea fails. So if we can't do that, how do we figure out the Broglie wavelengths for the whole baseball? Does it even have one?
It does. But we have to think about the object as a whole. Let's revisit that internal motion idea. The atoms inside are jiggling around randomly due to heat. But if the baseball itself isn't moving, the average momentum of all that internal jiggling is zero. It cancels out. That internal thermal energy doesn't contribute to the baseball's overall motion through space. It's translational momentum. And that's what determines the de Broglie wavelength of the object as a whole.
Ah, so we need to look at the collective motion. How does quantum mechanics handle something that complex, with trillions of interacting particles?
Well, surprisingly elegantly, actually. There's a standard technique in quantum mechanics for systems of many particles, like a molecule or, yes, even a baseball. It lets you separate the motion of the object's center of mass from all the internal motions, the vibrations, rotations, electrons whizzing around. You end up with two parts to the description. A center of mass wave function, let's call it XCM, that describes the motion of the baseball as a whole. It depends only on the average position, the center of mass coordinate. And then there's a separate, usually much more complicated, internal wave function, internal, describing all the relative positions in internal dynamics.
In the center of mass part, how does that behave?
What's really neat is that the quantum equation governing that center of mass wave function looks exactly like the equation for a single hypothetical particle. A particle that has the total mass of the baseball, m total, and the total momentum of the baseball, pupil, which is just its total mass times the velocity of its center of mass, VCM.
So the answer is surprisingly simple then. The de Broglie wavelength of the whole baseball depends only on its total mass and its overall velocity.
Exactly. The formula is the same one we started with, just using the total quantities. Oop object equals HP total, which is h m total a VCM. It describes the wave nature of the entire object moving as one unit.
So what happened to all those individual atomic waves we talked about? Where did they go in this picture?
They didn't disappear. They're all bundled up inside that internal wave function. Internal. They define the baseball's structure, its temperature, its rigidity, all its material properties. But crucially, they're mathematically decoupled from the overall translational motion described by the center of mass wave function. So, yes, the baseball does have a de Broglie wavelength as a whole entity, but it's an emergent property of its collective motion, not some simple sum of its parts.
Okay, this raises a huge question then. If the baseball does have a de Broglie wavelength calculated from its total mass and velocity, why have we never ever seen a baseball diffract? Why does our world seem so stubbornly particle-like? Solid objects, trajectories, not waves spreading out.
Right, and there are two main answers. The first one is just about the sheer scale involved. Remember, iptioik, macroscopic objects have enormous momentum compared to quantum particles, mainly because their mass, m total, is huge. Let's run the numbers for a typical baseball. Mass around 0.145 kilograms. Let's say it's thrown at 95 miles per hour. That's about 42.5 meters per second. Its momentum, PAP, is about 6.16 kilogram meters per second.
Okay, seems like a normal number.
Now plug that into HHP using Planck's constant. KJ is 6.626 by 10 joule seconds. You get a wavelength. Baseball in 1.08 to 10 U meters.
10 to the minus 34, that's staggeringly small. How small is that?
Okay, perspective. The nucleus of an atom, like a proton, is roughly 10 meters across. So the baseball's wavelength is about 100 trillion times smaller than a single proton.
Wow. Okay.
Now, to see wave effects like diffraction, you need an obstacle or slit that's roughly the same size as the wavelength.
So we'd need a slit 10 meters wide.
Exactly. Forget building that it's smaller than the fundamental length scale physicists even theorize about, the Planck length. It's physically impossible to probe something that small. So just based on scale, the wave nature is utterly hidden from us for everyday objects. You can see this trend clearly. Electron wavelength, maybe 10 U meters. Buckyball molecule, 10 U. Das mud, maybe 10 U. Baseball, 10 urium. The wavelength plummets as mass goes up.
Okay, the wavelength is impossibly small. That's reason one. You said there was a second, maybe more profound reason?
Yes, and this one is called quantum decoherence. Decoherence is the process where a quantum system loses its quantumness specifically, those fragile phase relationships that allow for superposition and interference because it inevitably interacts with its surrounding environment. No system is ever perfectly isolated, especially not something big like a baseball.
What kind of interactions are we talking about?
Constant interactions. The baseball is flying through the air, right? It's colliding with trillions upon trillions of air molecules every second. It's absorbing and emitting thermal photons because it has a temperature. It's interacting with the background radiation of the universe. Each tiny interaction entangles the baseball's quantum state with the state of the particle it interacted with, an air molecule, a photon. This entanglement effectively leaks the quantum phase information out into the vast environment. It's like the environment is constantly measuring the baseball's properties.
So it's like the Schrodinger's cat scenario again. The act of observing, or even just the environment interacting, forces a quantum state to collapse into a definite outcome.
Pretty much. The cat in the box in its superposition of alive and dead, is never truly isolated. Even one stray photon bouncing off it inside the box carries away information about its state. That interaction entangles the cat with the photon, and the photon flies off, spreading that information into the environment. The coherence, the "and" part of alive and dead, gets rapidly delocalized, spread thin across countless environmental particles. From our perspective, looking at just the cat, or the baseball, the coherence seems lost. The pure quantum superposition, alive and dead, effectively turns into a classical statistical mixture. Either alive or dead, we just don't know which yet. Interference effects, which depend on that coherence, get completely washed out because the necessary phase information is scrambled and lost to the environment.
And does this happen quickly?
Incredibly quickly for macroscopic objects. The decoherence timescale, the time it takes for the quantum coherence to be essentially destroyed, gets shorter and shorter, very rapidly, as the object gets bigger and interacts more strongly with its surroundings. For a baseball, it's practically instantaneous, far, far faster than any timescale in which you could even imagine trying to set up an experiment to see its wave behavior.
So our everyday classical world, it's not that quantum mechanics stops working. It's that its most striking features, like superposition and interference, are constantly being erased by the environment.
Exactly. Classicality isn't fundamental. It's an emergent property. It emerges from the underlying quantum reality due to this relentless process of decoherence. The universe is constantly monitoring macroscopic objects, forcing them into definite states and hiding their wave nature.
So are there any situations where quantum effects do show up on a larger scale? Any exceptions to this decoherence rule?
Yes. And they're fascinating because they show what happens when you can protect quantum coherence even in larger systems. These are the exceptions that prove the rule, so to speak. Think about phenomena like superconductivity and superfluidity.
Where materials conduct electricity with zero resistance, or fluids flow without any viscosity.
Right. These happen at extremely low temperatures. The cold minimizes the thermal vibrations, the environmental noise. Under these special conditions, huge numbers of particles, electrons in a superconductor, atoms in a superfluid, can actually lock together and enter a single coherent quantum state. They behave in unison, like one giant quantum wave. Another example is a Bose-Einstein condensate, or BEC. Here you cool a gas of atoms down to near absolute zero, and they collapse into the lowest possible energy state, effectively merging into a single quantum entity, a superatom, that can exhibit wave-like properties on a visible scale.
So these macroscopic quantum phenomena, while exotic, really drive home the point that matter is fundamentally quantum at all scales.
Precisely. The familiar classical reality we perceive is, in a sense, an emergent illusion. It's born from the constant decohering chatter of environmental interactions that washes out the underlying quantum weirdness for everyday objects.
Which leads us right to the cutting edge, doesn't it? Studying this transition from quantum to classical.
Absolutely. Understanding decoherence and the quantum to classical transition is a huge area of research. It reveals this fascinating picture where the difference between the micro and macro worlds isn't really about different physical laws. It's about complexity, interaction, and the fragility of quantum coherence in the face of a noisy environment. How big can we make something and still keep it quantum? That's a major experimental challenge.
So let's wrap this up. We started by asking if a baseball's wavelength was just the sum of its atoms' wavelengths, and we found out, no. The baseball does have a de Broglie wavelength, but it's a property of its overall motion, its center of mass. It's totally distinct from the complex quantum states of its internal parts.
Exactly. And maybe the biggest takeaway is that the solidity, the predictability, the very classicalness of our world isn't the fundamental baseline truth.
Yeah.
It's a consequence. It emerges because countless tiny invisible interactions are constantly observing and collapsing the quantum possibilities all around us, sculpting the reality we experience.
So the next time you hold a baseball or any seemingly solid object, maybe take a moment. You're not just holding a collection of particles. You're holding this incredibly complex quantum system, a whole symphony. But most of its weirdest, most quantum notes are just drowned out by the constant background noise of the universe itself. Makes you wonder, doesn't it, about observation, reality, and what else might be hidden beneath the surface. We really hope this deep dive gave you a fresh perspective on the quantum realm and maybe even the chair you're sitting on right now.